Hey students, Mr. Halpern here. So we're going to go into different types of substances that can dissolve into solvents, and we will talk about this for a little bit. We'll talk about ionic compounds first. We will be investigating different kinds of compounds dissolved in water. What you will observe is something that's happening on the macroscopic scale. So, for example, when you see salt being dissolved in water, you're looking at as a macroscopic process. However, in order to help us understand what's happening at the macroscopic level, we often draw a particulate level, which is what we've done before. Anytime you draw an atom, you're drawing a particulate level. So, an example of what's happening in the dissolving process of an ionic compound, when you're drawing it as a particulate level, you see the water molecule here as three different spheres. And just to remind you, water has a polar behavior in that it has part of it that is positively charged and part of it that's negatively charged. And what that does is it creates an interesting orientation between water molecules, and it creates these intermolecular forces called hydrogen bonds. The hydrogen bonds are formed by the positive hydrogens of one molecule and the negative oxygen of another water molecule. So what forces hold an ionic compound together? An example of an ionic compound is something like this. As you can see, and I'm blocking it, you can see this is an example of something like sodium chloride, right? This image here. So what holds those ionic compounds together? Well, it's ionic bonds. It's the attractive forces between the cation and the anion, in this case, sodium and chloride. Why do water molecules interact with these ions? Well, think about salt and think about water, right? Salt and water are actually very similar to each other chemically. Both of them have positive and negative parts of their molecules, okay? What do the dissolving ions have in common with each other? Well, if you look carefully at this image here, you can start to see what's happening with the dissolving process. And what I'd like to actually do is show you guys a video that shows this. So this is again salt, and what happens is water comes in and the negative oxygens are pulling the positive sodiums apart, and as you can see, the white hydrogens are pulling the negative chlorines away. And slowly this is pulling apart the crystal of salt. Okay. Again, the orientation is important. The negative chlorine is attracted to the positive hydrogens, and the positive sodium is attracted to the negative oxygens on the water. So back to our notes. So again, they're surrounded on four sides by water, these ions. And it kind of looks like this. I tried to draw out another way of seeing it in the particulate level. Obviously, sodium and chloride are no longer bonded to each other, so you have to actually break that bond. That takes a bit of energy. As we learned, the dissolving process takes a little bit of energy to break apart a salt, the ionic bond, but then it reforms this hydrated structure that you see here with water surrounding it, and that actually releases energy. What would evaporating water imply for the system? Well, if we didn't have as many water molecules in this system and salt is being dissolved, then you'd have less salt, or less water rather, and that water won't be able to surround the ions as much. And so potentially you could have less salt being dissolved, or if the salt was dissolved and now you're evaporating water, the salt could go back to becoming a crystal again. And you might have seen this if you ever have like a glass of water that has some sugar in it and it dissolves, you let it sit outside and it dries out, it evaporates the water. You can see the sugar crystals that have recrystallized again. So that's with ionic compounds dissolving in water. Why did they dissolve together? Well, because they had similar properties, right? Ionic compounds in water are both polar. And that leads to this next phrase that we often use in chemistry when we're dissolving things. The phrase is like dissolves like, and opposites attract. Okay? So like dissolves like means that polar molecules will dissolve other polar molecules. Conversely, we also have molecules that are non-polar, things that do not have a difference of charge across the molecule. And those non-polar molecules will also dissolve other non-polar molecules. To give you guys an example of this, I want to show you guys yet another video, short video. And in this video, it's a demonstration of a chemistry teacher doing an activity where he's taking some water, as you can see. He's putting it into the beaker. And we know that water is polar. So when we put in things like yellow food coloring and we swirl it around a little bit, we notice what? Does it dissolve? Yes, it does. We see that it's dispersed that color all throughout. We're taking another food coloring, red. Do we see that it dissolves? Yes, it does. What does that tell us about the food coloring? Well, like dissolves like, right? So that means that if water's polar and the food coloring is dissolving in it, that means that the food coloring is also polar. Here's another example, some more water. In this case, some Diet Coke. What do you think will happen? It dissolves, right? And we can see that. So then we know that Coke is a polar molecule. We can continue on. That's salt there. Does salt dissolve? Yes, it does, right? You can see it there. We pour all of these together and we have a big graduated cylinder. All of these polar molecules come together and they all dissolve into each other because, again, they're all polar, like dissolves like. Now we have some vegetable oil. What do you think is going to happen? We pour in some oil and some Coke, and what do we see? They do not dissolve in each other. If we see that the Coke was polar originally and the oil doesn't dissolve in it, what does that say about oil? What kind of molecule is it? It's a non-polar molecule. It does not dissolve in water. It does not dissolve in other polar molecules. Okay. This is, for example, a type of liquid that is an acid, and this does not dissolve in the polar Coke. It dissolved in the oil, actually. As we can see there, the oil is already starting to separate. So again, this is just an example, several examples of like dissolves like. The other part is opposites attract. What does that mean? It means that opposite charges are going to be attracted to each other. So in the case of water molecules and salt, the positive hydrogens on the water were attracted to the negative chlorine on the salt, and it pulled that apart. Okay. And then similarly, the negative oxygen on the water was attracted to the positive sodium on the salt, and it pulled that apart. And I have a question for you at the bottom there. I don't know if you can see it. My joke is, why do white bears dissolve in water? What do you think the answer is? Because they're polar bears. Yay! Anyway, I hope that was informative for you. The next part is dissolving gases in water. And this is not a particularly big section here. It's important to note that gases also dissolve in water, and certain variables affect them. So if you look at the graph on the left, the variable that we're looking at on the left is temperature. How does temperature affect the amount of dissolved oxygen in water? Well, as you see that we increase in temperature, right? As you go left to right, you see that there's a decrease in the amount of dissolved oxygen that can stay in there, right? So as you increase temperature, the amount of dissolved oxygen in a liter of water decreases. Conversely, as pressure increases over on the right-hand side, we see that there's an increase in the amount of gas that gets to stay in that liquid, okay? Here's another video of another chemistry teacher doing a demonstration of this. Oops. And we're going to go to the video. There we go. All right, so temperature and how it affects solubility. So in this case, this particular teacher is going to do 3 different demonstrations. One is at room temperature, another one is heating it up, another one is cooling it down. I want you to watch the reactions. Okay, at room temperature, this carbonated bottle has gas dissolved in it. When he opens it up, obviously it reacts. It spills all over the place, right? It creates a little mess. You can also see the vigorous release of that gas into the atmosphere, and it's not being dissolved anymore in the water. It's being released from the water, right? So that shows you again that at room temperature, you're going to be decreasing the amount of dissolved oxygen or gas that you can hold, okay? Now this is a bottle that has been chilled, right? It's much colder. How do you think that might affect the amount of dissolved gases? Take a guess. Well, will it be releasing as much dissolved gas, more dissolved gas than at room temperature? Less? What do you think? Let's see if he opens it and see if it's as vigorous. Ah, see, there's no mess whatsoever, right? There's a lot less gas that's being lost because it's colder. Colder temperatures for liquids can hold more dissolved gases. Let's take a look at the last one. This one has been sitting in a hot water bath, right? Any guesses on what this is going to do? You probably guessed it. It's going to go crazy. And that's the example there, right? So it was not able to hold very much at all of the dissolved gas because it was so hot. So just wrapping this up here. So the 2 factors that mostly affect the amount of dissolved gases or oxygen is temperature and pressure. How do they remove dissolved oxygen from water? If you increase the temperature or you decrease the pressure, both of those will decrease the amount of dissolved oxygen or DO. What are the requirements of dissolved oxygen for things like fish? This is an application of this. Fish and aquatic plants need oxygen. And sometimes on really, really hot summer days, you actually have a huge problem with the amount of fish that can survive because there's a lack of dissolved oxygen that can stay in that really warm water. So they need at least 3 milligrams per liter in order to survive. That's really a low level. This is just some examples of different types of fish that can survive in different amounts of dissolved oxygen. So as you see here, some fish can survive at really low levels. So like uh, black bullhead can survive at 1 milligram per liter. Some can you really need a lot more, like black crappie or the green sunfish need a little bit more. This is a picture again of the industry. We use a lot of water to cool generators, but that those generators transfer the heat to the water, and then we release that water into the environment. And if that water is too warm and it releases too quickly, it can decrease the amount of dissolved oxygen in the water and cause things like fish kills, which is a massive death of all the fish in the water surrounding the plant there. And that's it.